Okay, so I want to go through one more video, kind of the same idea here, um, of using the behavior of the x-intercepts, using the end behavior to kind of either get graphs or equations and just kind of finish up this page. So for number 4, there's lots of possible answers, right? And then we're just going to find 2 of them. So it says find 2 equations that have the following characteristics. So, oh, sorry. Dismiss that. Sorry. So when it says degree 6, and I know we didn't really talk a whole lot about that explicitly yesterday, but when it has degree 6, it means that the highest exponent would be the 6th power. Now, it's very similar to a power function that we know the end behavior, but it just leaves off the coefficient. So whether it's positive or negative, we don't know. But so we're looking for degree 6. So all the exponents are going to add up to 6. If it crosses the x-axis at -7, notice it doesn't say how does it cross. So we might know that it crosses like a linear function or more of like a cubic function, as long as it crosses and then just touches at 0. That touching at 0 means it's going to be like a bounce, right? Even. And then crosses at that 2√5, which is kind of an awkward value, but certainly could be one of our values. So let's go ahead and make y equals, and let's touch at x equals 0. So let's call it, let's say, x to the 4th power. That definitely touches. And then we want to cross at -7. So we want to make sure that we have, like, let's say an x plus 7, right? That would cross as a linear factor. And then cross at 2√5. So we just make the awkward x minus 2√5. So that's one possible answer. We could get a second answer by just simply making it negative, right? Just changes the end behavior, but doesn't say anything about that. That works. But now we can get a little more creative with our exponents. We could say maybe make it x to the 2nd power, and then make this one, let's say, cubed, and then this one a linear or a single multiplicity. Now, again, kind of just going back up to like adding up the exponents, like that would add up to the degree. So the degree of 6. So again, these aren't the only ones, but just kind of just refreshing our mind about the way the exponents affect the behavior. Okay, now for number 5, I've given you the graph, and so we're looking for certain things about the equation. And so I'm going to focus first of all on the behavior at 2. So in order for that to happen, it needs to have a factor of x minus 2. The only factors of x minus 2 would have an intercept at that spot. So if I don't see an x minus 2 or something that will give me 2 as a 0, I know it can't even work. So that eliminates that one. And I think that's the only one, because this one does have a 2, a 2, a 2, and a 2. Okay. We also know we only need one of them, right? So anything that has a higher power, which I don't see, would have been crossed out. Okay. Let's then, we'll come back to that one, because some of them have a negative, some of them don't, and that's not going to affect that 0. It'll affect the overall behavior. Let's now look at the x being at the intercept at 0. That means we can only have one of them. And again, I'm noticing all of the x's have 1, so that's good. So then let's go to our final one at, let's see, color blue, at x equals -3. 1, 2, 3. And again, for a factor at x equals -3, clearly I have to take out a again because it's the wrong one. So -3 would give you a 0 in b, so that's still a possibility. But -3 will not give you a 0 here. So that's out. -3 works here and here and there and there. Okay, so now we're down to b, d, and e. And then if I take a look at the behavior of all of them, I do know that it is even, right? There's 2 of them there. There's 1, 2 of them there, and there's 1, 2 of them there. So I'm down to those 3 choices. So now we need to look at end behavior. End behavior means that overall the thing has to be a positive function. So when I look at b, don't be, and when I look at b, don't be fooled. It is overall positive because this negative and this negative would multiply to be a positive. So that's the correct end behavior. If I look at d, if I factored a negative out of this term, that's going to make my overall function negative. And that's not the end behavior, so I can cross that out. And then my last one, if I factor this negative out, coupled with that negative, the overall end behavior is positive. So now I've got it narrowed down to B and E. So how do I decide? Well, that sort of goes up to that degree or the even versus odd behavior. It's because we're starting and stopping up here, both on top, overall it has to be an even function. And so when I look at that power, it's probably going to, like the degree is going to have to be an even number. And so when I'm counting degrees, I'm going to count like all of the exponents. So I have a exponent of 1 and 2, 3, an exponent of 4. That's an even number, so that would check out. But then I look here, 1, 2, 3, 4 also checks out. So they actually both work. So both B and E would be correct equations. Okay, so now number 6, number 6 really looks a little bit further into the semester because we're going to have to factor. And so I do want to talk you through this one just because, again, so when we factor this out, I'm going to factor by grouping. And don't worry, we're going to spend a lot of time factoring throughout this whole semester. But I'm hoping we do see that factor by grouping technique, that we can factor out x to the 4th power out of the first two, and a 16 out of this, a negative 16 out of the second two. So that gives us, I guess I can leave the f of x over here. That gives us two common factors, right? That gives us x plus 1 and then x plus 1. So now I'm going to factor that out. So I'm going to take that x plus 1 out, and that gives me x to the 4th minus 16. I think there's like a dead spot in my Chromebook or my tablet. Now, that's giving us one of the zeros, but there are more because x to the 4th minus 16 can factor further. So that's like a difference of squares. We could think of that as x squared minus 4, x squared plus 4. And that middle term that I have x squared minus 4 can factor further. So we have one more layer to this. So we have x plus 1, x minus 2, x plus 2, and then x squared plus 4. And so I have 3 real x-intercepts. Right? One of them comes from that factor of negative 1. Oh, there's the bell. One of them comes from the factor of 2, and one of them comes from the factor of negative 2. Now, the final binomial here, x squared plus 4, that's not going to give us any behavior along the x-axis. That's only imaginary solutions. So I can sort of temporarily ignore that. I'm only going to have those 3 zeros. So when I sketch this, I'm going to keep track of, there's a 0 at 2. There's a 0 at negative 1. And there's a 0 at negative 2. Okay. And my overall function's positive, so I know it must start up here. So then, as I'm graphing this, each of the behaviors are linear, right? Each of the multiplicities, that exponent is just a 1. So I know it has to intersect like a line. So I'm going to go down here. I don't know how low it's going to be, but as I come back up here and go back down there and end. And you might be wondering, well, what does this little like x squared plus 4 do? Well, it doesn't affect any behavior in terms of the end behavior. So I know it still starts up here. It doesn't do anything to affect the local behavior at the x-axis. So it's not affecting anything there. So I just kind of temporarily ignore it. I mean, in all honesty, the only thing it contributes to is finding that y-intercept. And there might be other pieces of the graph that change that might have a different little curve to it, but that behavior doesn't happen. at the x-axis. So I'm not going to have to worry about that. So I sort of just temporarily ignore it. And really the goal of this particular example is twofold. One, to remind us how to factor by grouping, and then two, to distinguish the difference. So even if you already had it in factored form, imaginary factors or factors that would give rise to imaginary zeros don't affect the local behavior or the end behavior. So I can sort of temporarily ignore them. Okay, so hopefully that makes sense, in that you have a good recollection of some things maybe we did last year, but the focus on Monday's quiz really should be keeping things in, like if I would have given to you already in factored form, and so just having to deal with what does that imaginary part look like. Okay, and then you don't have to worry about example 7. You are free to leave that one blank for this moment.